Welcome our next speaker, Yvonne Becherini, who will be talking about astronomy, astronomical data.
Yeah, we do have a pointer.
Do we have a pointer?
No?
We'll try to get it.
Or a mechanical pointer? No? No, not even. Okay. Is it working? Is it working? No?
Yeah, please, whenever you're ready. The pointer is coming.
Marcello has a point. As usual. Thank you. Will it work with this? No, but we have to put the... No, yeah, okay. Okay, but doesn't work for the slides, so, well, okay, at least we have the pointer. So, hi everybody, so my name is Yvonne Becherini. I'm a lecturer at Linnaeus University at the physics department. So, I'm here in Sweden since 2013, and I have established a group working in very high energy astronomy. So I will take you to a short tour to the universe now. It's quite far from diabetes problem, but okay. So I hope you will enjoy. So yeah, the participating people to this problems related to big data are myself, Michael Punch, which is a researcher partly working at Linnaeus University and partly in France, in Paris, at the Astroparticle and Cosmology laboratory in the center of Paris, and Sabri Plana from the computer science department. So first of all, what is astroparticle physics and what is very high energy astronomy? So astroparticle physics is a discipline which is a little bit at the middle between other disciplines. So the first is cosmology. Cosmology is the science of so understanding the Big Bang and the evolution of the universe. And then we have astrophysics and astronomy, which is the science, scientific topic, let's say studying the properties of planets, stars, and galaxies. And then we have particle physics, which is the study of the fundamental properties of particles and their fundamental interactions. So when we study the, universe, we have different kinds of messengers that we can use in order to identify what are the processes going on in the galaxy, in our galaxy, and beyond our galaxy. So in other galaxies, which can be very close to our or very far away from us. So suppose that a galaxy here is very far away, yeah, has a kind of mechanism which is able to produce photons. So the photons will travel through the universe, reach the Earth, and we will be capable of catching the photon component, the photon messenger from these sources. Then there could be the possibility of detecting neutrinos, which are very low mass particles, neutral low mass particles. And also, in some cases, we can detect the charged particles coming from these sources. So we are specialized at Linnaeus University in the photon band, and in particular, now it's working, so in particular in the very high energy photon band, the band of gamma rays. So here, for instance, you can see the plane of our galaxy, so the plane of the Milky Way, as seen in three different bands. So the first one is the infrared band. Okay, so this is the plane of our galaxy seen in the infrared band. This is how we see the plane of our galaxy in the optical band. And here you can see how we see the sources which are lying in the plane of our galaxy with the very high energy gamma rays. So very high energy gamma rays. So gamma rays are the most energetic photons that we get from the universe. It was 15 minutes, right? 10 plus 5. I saw 20 in the, yeah, so it has changed. Okay, okay, so this is where I was, okay. So we are specialized in the detection of gamma rays coming from the universe. And for instance, in Unsala, in Sweden, the Unsala Observatory near Göteborg, they are specialized in the radio detection of the radio photons coming from the universe. So how do we detect the gamma rays on Earth? So this is a gamma ray coming from a certain source in the universe. It interacts with the molecule of our atmosphere, and then it produces a cascade of electrons and positons, which in their turn produce again, optical photons which can be catched by telescopes sitting on the ground. So we participate to very big international projects. So the first one is the high-energy stereoscopic system in the Kalmarsalen Islands in Namibia. So we have 5 telescopes taking data 1 hour south from the capital, Windhoek. And so just to give you an idea of the data output of the current configuration of the HESS telescopes, it's about 6 terabytes per month. What do we do? So since I don't have so much time as I thought, I will not talk about science. Because it's fine. No, okay. So, so I will take a few minutes to tell you what kind of science do we do. So we are specialized in the study of active galactic nuclei, which are galaxies containing a supermassive black hole at the center. And then there is an accretion disk that I hope you can see. Maybe here it's better. There is light. So an accretion disk here rotating onto the black hole, and then there are these bipolar jets where we think particle acceleration is taking place. So as I said, so we have several expertise, let's say. We have expertise in data analysis, and we have also expertise in hardware development. When we do the data analysis, what we do is that we analyze the data coming from this array of telescopes in Namibia. Then we also are capable of analyzing the data coming from a satellite experiment, which is called the Fermilat satellite. And by means of our big international collaboration, we can also analyze the X-ray, optical, and UV data coming from the astrophysical sources. So that in the end, we have a complete snapshot of the photon component of our sources. So the second big experiment we participate in is the Cherenkov telescope array. This is an enormous collaboration. It's a consortium of, I think now we are at 35 countries all over the world. You can see here a map of the countries collaborating with us. And so we are about 1,200 people working in this project. So the aim of this project is to build 2 array of telescopes, one in Chile, and this array will contain 55 telescopes. So we are completely changing the magnitude. So we are going from 5 telescopes to 55 telescopes, and 20 telescopes in La Palma. And so for this project, what we do is to participate to large Monte Carlo simulations campaigns which are done in the grid, with the grid architecture. Then the third international experiment we are working in is the Alto Project. So this project is initiated at Linnaeus University by me, by an idea that I had in 2013, and that was kindly supported by the Crawford Foundation. So the aim here is to build, again in Chile, at an altitude of 5.2 kilometers, so a very high altitude experiment, an array here of 1,200 tanks of water and scintillator detectors. Sorry, I'm not very used to this kind of. Yeah. So what do we do for the moment with the money that we have? Is that we also do Monte Carlo simulations, and this is done basically in the Lund SNCC cluster. But the idea would be that we in the near future, transfer all these kind of simulations in the high performance computing center that we are going to build at Linnaeus University. So my last slide, so why are we big data? So because we have hundreds of terabytes of real and simulated data to analyze, and sometimes this data has to be shared between all the collaborators that we have all around the world. Then, so I tried to think about possible collaborations with the industry and IT companies in the theme of big data handling and exploitation. And so, yeah, I have finished. I think that one possible collaboration would be in finding solution for fast access of scientific data all over the world. So the question would be here, is it copying all the needed data, for instance, in your local cluster, the right solution? I don't think so. So is it better to invest on large local storage, or would it be better to benefit from a shared storage solution? Shared in the sense at an international level, not only in Sweden. Then another point would be to find solution on how to transfer data from remote locations of experiments, like for instance deserts or high altitudes, like in Chile at 5.2 kilometers of altitude, to computing clusters where data are processed. So this is a problem more related to transmission of large data sets. And then a last point is the possibility to study solutions which will ensure that no data is lost during, really at the time you're writing on the disk. Okay, so that's all.
Very good. And thank you. And I'm sorry for confusing you. Do you have other colleagues here who are in the work package today who could introduce themselves?
No.
Nobody else is here. Okay. Well, we have 5 minutes for questions, and please feel free to ask them in Swedish if that's easier. We do speak Swedish, most of us, at least. Yeah.
Thank you, Yvonne. That was very interesting and exciting. We've all seen so great inventions helping our daily life coming from physics research in the past. So my machine here wouldn't exist without physics invention in the beginning of the 20th century. Can you give us a projection of the research that you're doing right now and the impact of that research on the daily life in the future, be it a direct impact of the results of findings or an indirect impact of the technology that you're developing within the project, having an impact then on our lives?
So what we do, our research, I hope you can still hear me, our research is, how to say, fundamental research, okay? So it's research for the benefit of everybody. So it's knowledge-based research. And so, I mean, I don't think that, for instance, understanding active galactic nuclei will have an impact to our daily life. But if you think that, for instance, the CERN, the developments that were done at CERN for the accelerator, for the current accelerator, but also for the former accelerator that was running until the year 2000. So the World Wide Web was invented at CERN, right? So and I think so. There's more technology-driven, how to say, topics, I would say. So, for instance, the 3 points that I'm listing here are, are important points which are, I think they're not important only for astronomy, right? Because in principle, if you have large international collaborations and you need to share the data, you need to ensure that this system is working for everybody. So in the end, I think that sometimes in astronomy and in particle physics, we have almost the same technological problem that people face every day, but on a larger scale.
Thank you. Other questions, please? Yeah. All right. Well, then we'll continue during the break, which will last 10 minutes. But then we'll have a possibly longer discussion time before lunch and during lunch as well. Thank you very much for this session.